Hi class, we're going to continue with section 9.1. We're going to look at a new concept called the critical values for the Pearson correlation coefficient. So once you've calculated R, which is the sample correlation, so that's our sample correlation coefficient, you're going to want to determine whether there's enough evidence to decide that the population correlation is significant. In order to do this, we're going to use a table. And this is the one spot in our course where we can't use StatCrunch as an alternative. This is only the information is only in a table, and I'll show you how to access that table here shortly. So you're going to go to that table and find a critical value based off of a level of significance, and then you're going to compare that critical value to your R. So let's look at this example number 7. Find the critical value, and for the blood pressure example, so the values you're going to need, you need N, which in this case is 10. There was 10 men in the study, and you need the alpha, 0.05. And then we also need our R, which we found in the previous video, 908. Okay, so now we go to the table, and that table is located, if you go to Canvas, under Modules, it's where all the class notes are. So I click on Class Notes. You've probably seen it already. Down there at the bottom, Stat Tables. So I click on that. And it's the very last table. So maybe you've been trying some of these out with previous problems, but the one we need is that Table 11. Table 10 we'll never use, but it's this Table 11 on the right. Okay, and so for this problem, N is 10, so I go down to 10, and then alpha 0.05, that leads me to the number 0.632. That's the critical value. Okay, so now I'll go back to my handout and write that down. Critical value, 0.632. And then the way this works is that bullet point number 3 above, right? If R is greater than the critical value, then there is enough evidence to conclude the significant linear correlation. And notice it's absolute value of R. That means if R is negative, just ignore it. Right, so don't do any negatives. It's just comparing R to the critical value. So here we have R is greater than that critical value. So that implies that we have enough evidence, excuse me, or there is, let's just say, a significant correlation, linear, okay, between the two variables, okay, in the population. So the key, I guess I should say that, in the population. We know it's in the sample, but we're making an inference to the population. All right, let's try another one, just doing everything that we've done so far in this section. So we have a new set of data. We're going to find the sample correlation coefficient, describe the type of correlation, and then use that correlation table. Okay, so let's load the data. Let's see. We're going here, back to StatCrunch, and then there is the data. This is the soccer player one. So I load the data in there, and then remember where to go to get everything. You go to the stat, regression, simple linear, X is the weight, Y is the time, compute. That gives me my R. Here we have R is negative 0.983. So that's all I'm after, right? It's that 6th line down, R correlation coefficient, negative 0.983. Okay, so I'll write that down. Negative 0.983 is the R. And then what kind of correlation is that? Well, it's negative, and that number is very close to 1, right? So this will be a strong negative linear, don't forget that word, correlation. Okay. Now we're going to use the table of critical values. to decide about the population. R is so strong, I mean, I know it's probably going to be fine, but let's just find that value anyway. So now we look at, let's see, we have here n equals 12, right? And alpha is 0.01. So now I go to that table. N equals 12, and then that second column, I'm seeing a 0.708 on that. Is that what you see? All right, I'm just going to go with 0.708 for my critical value. Now notice, again, like I said before, R is negative, but ignore the negative. So I'm just looking at 0.983. That's bigger than 0.708. So that means that the correlation is significant. In the population. Okay. And that's it. That's all we got to do. Okay. So you see some of those problems in my lab. Just use that table and you should be good. One more thing we'll look at in this video is correlation versus causation. So the fact that two variables are strongly correlated does not in itself mean that there's a cause and effect relationship. That's different. So strong correlation does not imply a cause and effect necessarily. So when there's a significant correlation, you should consider some of the other possibilities, right? Doesn't really mean that one causes the other necessarily, right? So, I mean, it could be, right? Does X cause Y? Or maybe it's the reverse. Maybe Y causes X. That's a possibility, right? Or it's possible that the relationship between the variables is caused by a third variable that's not even in the study, right? Or a combination of several other variables. So those are called lurking variables or confounding variables, we've called them in the past. Right? They're variables that aren't even in the study, but they're the true cause of the link that we're seeing. Or maybe it's just a coincidence. All right, there's always that. Okay, so here's an example. Breaking news. Eating ice cream causes shark attacks. So notice the word there is using causes. So this one's kind of a silly example, right? Because we all know that eating ice cream probably does not cause shark attacks. But a recent study showed that there was a strong positive linear correlation between ice cream sales and shark attacks in a certain beach town. And we have proof of it. Here's the scatter plot, right? We have ice cream sales as the x-axis, number of shark attacks on the y. As ice cream sales increase, so do the number of shark attacks. So if you don't want to get attacked by a shark, don't eat ice cream, right? That's the conclusion. So do you think X causes Y? Like eating ice cream causes a shark attack? Probably not. I would say no there. What do you think? Do you think Y causes X? As people are getting eaten by sharks, do people start eating more ice cream? That sounds a little strange, so I'd probably say no there. Is it possible that the relationship between the variables is caused by a lurking variable? Is there a third variable that's not seen here that's actually the true cause of the relationship? And yes, probably so. I would probably assume that that is hot weather. Right. In the summer months, because in the hot weather, people tend to eat more ice cream. They also tend to go into the water more to cool off, hence an increase in shark attacks. Right? So there is an example of that lurking variable that's causing the relationship. Or I guess it could be a coincidence. I guess maybe, but I would think not. Okay, give 9.1 a try. If you have any questions, let me know. Hope all is well, and I'll talk to you in 9.2.